Okay, and we're back to the slides where we're going to talk a little bit about chemistry now. So enough course logistics, let's get to the chemistry. So this first slide is just very, very basic, and the purpose of it is just to make sure we're all on the same page. To be honest, I have no idea what preparation you all have in terms of chemistry. Some people don't take chemistry in high school, some people do. So just to make sure we're all on the same page, let's start at the very basic level. So when we talk about chemistry, really what we're interested in, what chemists are interested in, is the chemical composition of things. And that starts with, at the most basic level, the fact that matter is composed of atoms, okay? So an atom structure is composed of some sort of nucleus. Well, not some sort of, it's composed. All atoms have a nucleus at the center. So this nucleus is composed of protons and neutrons. These are the basic subatomic particles that are present in the nucleus. Lots of really interesting history as to how we know this, because you can't see an atom. An atom is incredibly tiny, but just believe me that they're there, okay? And then there are also electrons orbiting the nucleus. You can think of it loosely like planets orbiting the sun in the solar system. That's a very inaccurate way of thinking of it, but it works just to have a picture for your mind's eye. So the electrons are orbiting the nucleus. Okay, so if we were to draw a picture of this, we have the nucleus, which is composed of protons and neutrons that are all clumped together, held together by what is called the strong force, one of the 4 elementary forces of nature. So let's just draw, that's a big atom, that's a lot of stuff, but so this is protons and neutrons. And I should mention also that protons are positively charged, which don't really worry so much about what that means physically, like what does it mean to be positive or negative or neutral. Just think of, like magnets, opposites attract, likes repel, and so on. So these are positively charged. And then electrons are, that's supposed to be an arrow, are negatively charged. And then neutrons, as the name implies, are neutral. So not charged at all. So you can kind of see some of the underlying forces that are holding an atom together, where positive and negative things are going to be attracted to each other. So if there are electrons orbiting the nucleus, the electron is going to be attracted electrostatically, we say, or it is attracted to the positively charged protons in the nucleus and orbiting at a set distance. Why it doesn't just collide with it has to do with a lot of quantum mechanics. We don't really have time or interest in this course to go over that, so just take it for given, or to take it as I say, that electrons are orbiting the nucleus like so. And for an element, so what makes an atom and an element different? This is an atom with a specific number of protons in the nucleus. So something like carbon, an atom of carbon, so carbon is an element, and an atom of carbon is very specific. So I guess I'll write this down so I'm not just talking. Carbon, the elemental symbol C, nice and easy to remember. This has 6 protons in the nucleus. And because positives attract negatives, to maintain a neutral charge, which is something that atoms in general want, just to maintain electroneutrality or a neutral charge, these 6 protons will then attract 6 electrons that orbit that carbon nucleus. Another example is something like oxygen is another element. O, another easy one to remember. This has 8 protons. And because it has 8 positive charges in the nucleus, it will attract 8 electrons. Okay? This may seem very minute, very inconsequential, because who cares if carbon has 6, oxygen has 8? Does that really make a big difference? Just 2 protons and 2 electrons? But you have to think, on a macroscopic scale, there are, trillions upon trillions upon trillions of atoms that we interact with. So these very minute differences add up to be a very large difference on a large macroscopic scale, where something like carbon in its elemental form is like graphite or diamond, solid materials that are relatively hard and brittle. Well, diamond's kind of different, but graphite is very hard and brittle, whereas something like oxygen on a macroscopic scale is a gas that we breathe in to live. So very, very different physical properties that result from these minute chemical differences, okay? And the real purpose of why I'm going over all these details of atomic structure is ultimately leading to what we're going to talk about in this course. We're not really going to be talking about atoms and elements a whole bunch. This is probably the only time, hopefully the only time, I will draw this picture of an atom. But what we're going to talk about are molecules and compounds. So what these are atoms that come together to form more stable environments or structures around the atom. Okay, so what I mean by this is it's actually fairly uncommon to find a certain element all by itself in nature. So take carbon, for example. Sure, carbon can exist as diamonds or graphite, but as you might be well aware of, there isn't just a plethora of diamonds sitting around or graphite. A lot of the carbon is tied up in different forms. So an example of this would be something like carbon dioxide, a gas that's in the air that we breathe. So carbon and 2 oxygen atoms come together to form a molecule that has vastly different physical properties than something like just oxygen or just carbon, okay? And the distinction between molecules and compounds isn't so important for this class, but something like a compound would just be a different way for atoms and elements to come together. So rather than explain the differences of chemical bonding and that sort of minutia that would ultimately just bog us down in this course, we're going to think of molecules and compounds just in terms of elemental symbols, or rather chemical symbols. So this is as far as we're going to go in terms of chemistry in this class. I'm not going to draw molecules for you. So for instance, when we get to like polycyclic aromatic hydrocarbons, we're going to talk about something like naphthalene, which is a very common polycyclic aromatic hydrocarbon, which if you don't know what that is, I will define it later. I'm assuming you do. It's a pretty big topic in the realm of firefighting, I would assume at least. But this has the chemical formula C8H10. It's a 0. So obviously this molecule will have a complicated molecular structure that is certainly interesting to think about for a chemist, but for us, we don't need to think about it. So this is as far as we're going to go. We're just going to talk about chemical symbols and keep it at this very basic surface level, okay? And then the very last thing I wanted to go over on this slide was the idea or the concept of ions, which is something that we'll inevitably run into and bump into. So I just want to clear the air with that. That way we aren't confused later on. So what an ion is is an atom can be just a single atom, or not of, or molecule with an imbalance of protons and neutrons. Of protons and electrons, excuse me. Wow, I'm really botching this whole definition here. I'll get there eventually, I promise. So it's an atom or molecule with an imbalance of protons and electrons. And this is really going to be a recurring theme, especially when we get to water chemistry with wildfires, because something like chlorine, see, I already made a mistake. That's how simple it is to do. So chlorine is an element. If I write it just like this, it is elemental, or rather atomic chlorine with very specific chemical reactivity that we'll see in our second lecture here. And then also something like chloride. We don't need to know the nomenclature or how to name these things, so don't worry about that. But just know that when I write this same elemental symbol, but now I put a minus in the superscript, that means it has one extra electron compared to the number of protons that it has. So neutral chlorine, equal number of protons, neutrons, protons, electrons. Chloride, negatively charged chlorine, has an extra electron, okay? And this is important because it will drastically change the chemical reactivity of the element, and will be a very important distinction for you all to make, because we will learn about neutral chlorine atoms in the stratosphere and how that interplays with the chemical processes that occur up there. And we'll also talk about chloride and in like natural waterways. And the two are very, very different, okay? So I just wanted to make it clear that you'll see lots of different ions with positives, negatives. So just keep in mind when you see those, it is very deliberate and it is very intentional when those pluses and minuses are included, because it will very, very drastically change the reactivity, and it's an important detail to consider in chemistry, okay? Okay, so let's move now to some information that's probably, not probably, it is a lot more relevant to what we're going to be talking about in this course. So in a wildfire, what chemical processes are occurring? So in chemistry, the way we denote a chemical reaction is just with the general form. Let's say A and B are two chemicals that react. We say when they react, we just draw an arrow. That's supposed to be an arrow. I feel like I'm making it worse by writing over it. But arrow, and then goes to some products, let's say C and D. This is a very typical way for chemists to describe a chemical reaction. So in a wildfire, the most common chemical reaction, I wouldn't say it's the only chemical reaction, but it's certainly the one that is most relevant to our class, is combustion. So combustion always has the same general form, where there's some hydrocarbon fuel. I'll call it CXHY, because carbon and hydrogen can be present in differing amounts, and there might also be some other elements present. Like there could be oxygen or nitrogen or sulfur. This sort of stuff isn't so important. Focus more so on the carbon and the hydrogen. So we'll just say that, and it reacts with oxygen. That is a necessary criterion for a reaction to be considered combustion. It must react with oxygen, and in doing so, it forms the same two products, carbon dioxide and water. And then these are gases. We don't need to get into that. Let's not worry about that. We'll touch on states of matter later in this lecture, but for now, this is just the simplest form of a combustion reaction. So just to give an example of the simplest hydrocarbon, methane, CH4, so this is methane. If we were to combust methane, the way we could write this down on a piece of paper is we would say methane reacts with O2 to form carbon dioxide and water. And I'm including some 2's in here just because the law of conservation of mass says that we can't create or destroy matter. So I just am doing this to make sure that there's an equal number of oxygens, hydrogens, and carbons on each side of the equation, okay? Not super important. I'm not going to make you balance equations, but just as a chemist, it's a detail that I feel is important, necessary, whatever. So this is, in general, a combustion reaction, and that's what's happening in a wildfire. So more relevant to consider, wildfires aren't burning methane. Not always. I mean, certainly it can be involved to some small degree, but to a much larger degree, wildfires are burning plant matter. So what is plant matter composed of, and how does that impact how it burns? That's a very interesting question to ask. So plant matter can be abbreviated as carbohydrates, essentially. So carbohydrates are sugar molecules linked together. So the most simple sugar molecule is glucose. So plant matter, if we wanted to give our best attempt to reduce it down to just a single molecule, the best approximation we can make is to say, hey, it's glucose, C6H12O6, something you might remember from high school biology class. Is this perfectly representative of plant matter? Definitely not. And we'll talk about some of the minutiae of how different vegetation types burn, what sort of products result from that. But this is just to give you a general idea of how we can describe the combustion of plant matter. So the rest of the equation, or the reaction for combustion, looks like so. I believe that's balanced correctly. So we can describe plant matter as this process. We're taking glucose and we are converting it into carbon dioxide and water, okay? And to the skeptical student in the class, this might ring some bells, raise some alarms, where you might think, well, hang on, I know CO2 is a gas, water can be a gas or a liquid. We're going to assume that because fire and combustion is very what we call exothermic in thermodynamics, or it releases a lot of heat, that these are going to be really, really hot. So it's likely that the CO2 and the water generated from this reaction are going to be in the gas phase. And you might think, well, hang on, these are colorless. I can't see water vapor or carbon dioxide very clearly. Well, you can kind of see water vapor, like if you're boiling a stove pot, but it certainly doesn't look like the wildfire smoke plumes that are so attributed to, or so correlated with wildfire. So what the heck? What's going on? So what this combustion reaction represents is sort of an ideal scenario. This molecule, carbon dioxide, is incredibly stable. And to a degree, water is also very stable. But what this reaction is representing is the most stable transformation, the most ideal transformation in a combustion reaction. If this reaction were to occur as perfectly and ideally as possible to make the most stable products possible, it will only form CO2 and water. But obviously, that is not true, because when we think of wildfires and smoke plumes, they're very black. There's a lot of different compounds and molecules associated with them. And the reason that wildfires do not only produce two things is because, one, well, the chemical composition of plants are certainly going to be much more complicated than just glucose molecules. And then also, in the real world, the chemical reaction is not going to proceed ideally as we would write on paper. There's going to be a lot of different byproducts in the process of taking this complicated molecule of glucose and converting it to CO2. So some common byproducts that are going to be formed along the way include stuff like carbon monoxide or something like polycyclic aromatic hydrocarbons, where some of these glucose molecules can bump into each other and form molecules with more carbon in them. So I'll just say etc. just because there are so many different byproducts that can form. There's a lot of these intermediates that form on the way to becoming CO2, and because this is not a closed system, it is simply open to the atmosphere, these things scatter throughout and don't necessarily completely burn to become CO2 and water. And this is really where the meat of our course will be focused on is what are all these different byproducts that can form? What do they do to the environment, to the atmosphere, to water, to us when we breathe them in? And it's a really rich and interesting space to explore, okay? And we will provide, or we will look at a more exhaustive, let's say, list of the various things wildfires can produce. So this is certainly not exhaustive. It is two things that I just randomly thought of. So first, let's think about the physical properties of wildfire smoke. And really where I'm going with this is that the components in smoke, or the compounds produced in wildfire smoke, exist almost entirely as what is called particulate matter. And particulate matter you may have seen in like some air quality or weather reports, abbreviated as PM. So I will do so probably several times throughout this lecture. PM, particulate matter, same thing, okay? And the reason for this is because a lot of the things fire produces are not really stable as single molecules, like something like CO2 or a molecule of water vapor might be. You could even make the argument water vapor doesn't even exist in a stable state as a single molecule. It likes to clump together. And that's the same for a lot of the things produced by fire, is it likes to clump together into particulate matter. So when I say particulate matter, the way it is defined is as small solid and liquid particles suspended in the air. So notice no gases. Wildfire smoke is almost entirely solids and liquids, as little teeny tiny particles that are floating through the air. All right, and when I say small, how small is small? So let's put some numbers to this. So particulate matter is on the order of 10 nanometers. I'll give some context for these units in a second. 10 nanometers to about 100 micrometers. I guess I won't use the mu symbol, I'll just spell it out. Micrometers in diameter. So we can approximate these particles to be spheres. So 10 nanometers to 100 micrometers in diameter. So when I say nanometers, that is 1/billionth of a meter, so incredibly tiny. So to give you an idea for some size here, so a human hair is about 70 micrometers. Obviously, I'm talking about the width, not the length. They can be much longer than that. But if you think of a human hair, you can just barely see it, and that's about, on average, 70 micrometers across, or if you think of it as a cylinder, the diameter of that cylinder would be about 70 micrometers, or the thickness of it. Hopefully you get the idea of what I'm trying to say here. So the upper limit is already what we can barely see, or at least I can barely see with my eyes, maybe a better eyesight than me. But that's the upper limit, is so incredibly tiny. And then 10 nanometers is going to be orders of magnitude even smaller than that, and totally invisible to your eye. So particulate matter is very, very, very tiny particles that are in the liquid and solid phase. So you might think of them as gases, but that's not actually true. They're so small that you might think, oh, it's just in the gas phase, but it's a little teeny tiny droplet or crystal of solid liquid matter, which is really interesting, I think. And this sort of begs the question, okay, if it's solid and liquid, why doesn't it just settle out? Because of gravity. Why does it go into the atmosphere and react and do stuff? So this is not so important. I'm not, well, it is kind of important. It is an interesting detail to know. So scratch that. This is important to know. And, we're not physicists, but this is still a good thing to understand. I guess I'll go back to black. So they are suspended in the air. So the question is, how is PM suspended in air? What the heck? It's solid and liquid. Why doesn't it just fall out of the sky? And this is because of something called Stokes' law, which basically was developed to describe the drag force of flow of liquid over a particle. So this describes the drag force, or if you think about it, think of liquid flowing over my fist. What is the force my fist will feel from the liquid flowing over it? I reformulated my definition here. I like the wording of this one better. So describes the Stokes' law describes drag force on a solid particle suspended in a liquid medium, which you might think, why would that apply here at all? Air is not a liquid, it's a gas. But you can model air flow as a liquid. And in fact, a lot of atmospheric models, which are very accurate, by the way, entirely operate on the assumption of treating air as a flowing liquid. Okay, so this really applies, like it's maybe not a perfect representation, certainly not a perfect representation of what is actually going on, but it works mathematically, and that's the important part. So Stokes' law describes a drag force on a solid particle suspended in a liquid medium, and basically what it shows is that the drag force, or the force that this solid particle feels in this liquid medium, or to put it in context of our discussion here, the force a particle of particulate matter will feel in the atmosphere is going to be proportional. So this is the proportional symbol. It looks like the Greek letter alpha, but it's just meaning proportional to the particle's diameter. Okay, so the smaller the diameter, the smaller the drag force. And this is really important in understanding why particulate matter can be suspended in the air and not fall out of the sky, because for particulate matter, the diameter is so tiny, the force of gravity pulling it through air towards the surface is also very, very tiny, and as a result, the natural air currents that exist keep it afloat, and in some cases bring it up very, very to high altitudes. So let's just finish this thought here. Hang on. Okay, so for particulate matter, just because it is such a small diameter, it does not settle out of the atmosphere because the force of gravity pulling it through this liquid flowing medium that is air is so tiny that it doesn't actually move towards Earth. It just stays in the atmosphere. And I think I just realized something. I'm glad I realized this earlier rather than later. I forgot that I have my webcam recording, and I think I put my face in the bottom right of the screen, so you probably could not read what I just wrote. I'm going to move it over here. So let's just keep in mind, let's block off this bottom right-hand corner. Hopefully I'm not cutting anything off. Hopefully that square is a good approximation for how much area my head takes up. So hopefully, yeah, hopefully it wasn't too bad. Oh, and I also realized a mistake with this relationship. It's actually proportional to the diameter squared, so it's a very, very strong relationship, okay? So TLDR, Stokes' law, is how we can describe why particulate matter does not settle out of the air and it stays suspended for us to breathe or for other chemical atmospheric processes to occur. All right, so now let's talk about some relevant sizes with particulate matter, just because I think it's always useful to have a picture for your mind's eye to think about this stuff. So let's think about some relevant sizes of particulate matter. So let's think about raindrops specifically. So raindrops, as we maybe are aware of, can be suspended in the sky as clouds, and once they get too big, they fall out of the sky as rain. So they can range in size from about 2 nanometers, so very, very, very tiny, all the way up to about 100 microns. That upper limit, I said I wasn't doing the mu thing, hang on. 100 microns, or micrometers. Oh, I'm doing so many. I'm trying to avoid jargon in these lectures. So micrometers. So, think like about the width of the human hair. So this is about the size range for raindrops, and on this lower end, they are very comfortably suspended in the atmosphere because of Stokes' law and the fact that their diameter is so incredibly tiny. And then here, once they get to about 100 micrometers in diameter, this is when they start to fall from the sky as rain, okay? And like I said, the reason why I'm giving you this size range is so you can sort of think about some of the relevant sizes that we'll be discussing in our discussions on like tropospheric and stratospheric chemical processes. So now let's talk a little bit about some categories or delineations. Categories might be a better word, but whatever. Here, I'll do even more basic types of particulate matter. So for those of you who maybe are interested in air quality reports or weather reports, you maybe see particulate matter defined as like PM10 or PM 2.5, and that's because that we'll talk about what the 10 and the 2.5 means, but really what that is it's breaking particulate matter down into coarse particulate matter and fine particulate matter. So coarse is often referred to as PM10, and this is sort of the particulate matter with diameters ranging, that's an R, not an S, ranging from 2.5 micrometers. Okay, I'm tired of writing micrometers every time. In science, we give it the abbreviation of the Greek letter mu, which is what I'm trying to write there. So that is mu and then a lowercase m for meters. So 2.5 micrometers. And as I say that, I write like the worst mu imaginable. So micrometers to 10 micrometers. Okay. And some examples of some coarse particulate matter is something like dust from sand. So if you think of like wind striking the surface of the earth, and kicking up a bunch of dust into the air. Some of that dust can remain for relatively long periods of time. And dust and dirt can be abbreviated as silicates or aluminosilicates. Generally, SiO2 is how it's commonly abbreviated, but there can be like aluminum, there can be more oxygen relative to silicon, but not super important for us today at least. We might talk a little bit more about this when we get to our soil chemistry lectures, but just know that a common example of coarse particulate matter is something like dust, okay, where it's a little bit bigger, tends to settle out a little bit more quickly, which one thing I should clarify here is that the whole tangent I went on with Stokes' law wasn't to say that particulate matter doesn't ever leave the atmosphere. It's just that the force it feels from gravity is so small, it takes a very, very long time for it to settle out of the atmosphere because of gravity, okay? So something like PM10 settles down a little bit more quickly, whereas something like fine particulate matter, or often abbreviated as PM2.5, this tends to settle out much more slowly, as you can imagine, because it has a much smaller diameter. I'm getting ahead of myself, but let's define this first. PM2.5 is diameter less than 2.5 micrometers, okay? And I realize I didn't give very many other examples of coarse particulate matter, so let's give some more examples of each, just to give you an idea of what we're talking about when we say coarse versus fine particulate matter. And then we'll also talk about why are we making this distinction. So other types of coarse particulate matter might be something like soot. So this is largely carbon, just elemental carbon, so usually produced from incomplete combustion of fuels. So soot is certainly present in wildfire smoke. And then also think like semi-trucks, those big smokestacks that they have emit that black smoke. That black stuff is carbon or soot, and it can be very, very large in diameter and fall under the category of coarse particulate matter, okay? And I should point out that this is often called elemental carbon, because as we'll see when we get to fine particulate matter, there are other types of carbon that can be suspended in the air as particulate matter. But this is often called elemental carbon. Another type of coarse particulate matter would include something like water or mist is a good example, where this is suspended H2O droplets in the air. Remember, these are all as solids or liquids. And for fine particulate matter, we can have soot again. So soot has a very large range of diameters that can be present. So soot can fall under the category of both coarse and fine. Another example would be something like organic carbon. So this is the other type of carbon that can exist as particulate matter. So when I say organic carbon, I'm specifically referring to the field of organic chemistry, which doesn't necessarily mean like natural or good for you, as the word organic typically connotes. Really, all this means to a chemist, at least, is that it is the presence of carbon and hydrogen in some amount. So organic chemistry is the field of chemistry that's very, very, very centered around carbon and hydrogen bonds. Certainly there's other things that can be present, like we can have oxygens, we can have nitrogens, we can have sulfurs, but basically what I'm talking about with organic carbon is carbon bound to hydrogen. And if you want to get like really persnickety about the delineations here, something like CO2, something that exists very naturally, you would think is an organic molecule. This is actually considered an inorganic molecule because there's no hydrogen bonded to carbon. It's just oxygen. So to a chemist, organic means something different than what you might see at the grocery store. Even organic at the grocery store doesn't necessarily mean what it's advertised to mean, but that's a topic for outside of this course. And other types of fine particulate matter would include something like sulfates. So this is, as the prefix sort of indicates, stuff with sulfur, which is an element denoted by S, the chemical symbol. And sulfates specifically refer to like SO3 or SO4. And usually these are going to be ions, so we give them these like 2- charges as a superscript. Don't worry too much about why, but just know that there are 2 extra electrons for all of the protons that are present on these sulfur and oxygen atoms, okay? And then we can also have stuff like nitrates, which are really important. So this would be stuff that's often abbreviated as NOx or NOx. The X simply denotes that there can be a varying amount of oxygens bonded to the nitrogen. So it could be NO or NO2, NO3, N2O5, N2O4. There's a lot of different variants. And rather than give a category for each one of those, we just lump them together and call it nitrates, okay? And by this point, you might be wondering, why am I droning on about all of these different categories here? Well, it's because we're going to touch on a lot of this stuff in our course, where the fine particulate matter specifically, this stuff is very toxic, which is usually the one that you need to be more wary of, like in an air quality report. You're going to care, or if to an air quality expert, they would be much more alarmed at a high level of PM 2.5 than they would be a high level of PM 10. And the reason for that is basically because smaller particles, or rather matter in general, wants to exist as large clumps. So if you think of like dirt on the ground or rocks, it's all clumped together pretty big. And the reason for that is because larger aggregations or larger aggregates of matter have more matter on the interior of that particle. So picture like a rock about the size of your palm. Only the stuff on the outside is exposed to the air and can react with stuff. The stuff on the inside is all relatively protected, okay? And that's generally a favorable form for matter to take up. So matter typically does not like to exist as really, really teeny tiny particles with, let's say, a diameter smaller than 2.5 microns. It's going to be relatively reactive in that state, because it wants to maximize how much matter is packed inside of it rather than being exposed on the outside. It's something that we call a surface area to volume ratio. These fine particulate matter particles have a relatively high surface area to volume, meaning of the matter they're composed of, almost all of it is exposed on the exterior and can react with stuff. That's generally very unfavorable. So fine particulate matter tends to be very, very reactive. So if you breathe it in, or if it is exposed to the atmosphere, it will react and do stuff, oftentimes not good stuff, which is really what we're going to be focusing on throughout this course. So the reason why I'm droning on about particulate matter here is because it is almost entirely where the interesting chemistry happens in wildfires is the particulate matter it forms, or rather the particulate matter that is formed by a wildfire, how it reacts with other things in the environment, okay? And I should also mention that these examples I gave down here of fine particulate matter are going to be very relevant for our discussion of wildfires. Sulfates admittedly not so much, but the rest of these, yes. So let's get now a little bit more granular and focus in on specifically wildfires and particulate matter, okay? So I did this on the previous slide. You saw some examples of common particulate matter in the atmosphere. So let's think about now what's present in a wildfire. So I'm just going to give you a heads up. The next slide will be a lot. There's a lot of data on it, but we're going to parse through it very methodically and give you an idea of what sorts of atmospheric changes occur because of wildfires, okay? So in this data set, what this is these researchers down here were analyzing the PM 2.5 species present in the air during a smoke wave. So this was 24 hours, I believe, after a wildfire, or while a wildfire was burning. They were constantly measuring the chemical composition of the atmosphere in their vicinity for these various elements, compounds, etc. Okay, so what we have here is the particular species that they've detected, so things like aluminum, arsenic, bromine, calcium. And it's important to make the distinction here that it's not like there's solid aluminum, like it's not like you ground up like a Coke can that's made of aluminum and threw it into the air. When we say aluminum, we're just detecting the element, so it could be present in some other compound. Because aluminum is a very common element in dirt and soil, it's likely going to be some form of aluminum that's associated with dirt. So it's not like wildfires and plants are producing aluminum. That's not what's happening here. We're just detecting the element aluminum. And something like arsenic, it's not just like elemental arsenic, it's going to be in some form. Same with bromine. It's not going to be the elemental form of bromine. Hopefully you get the point I'm making here. But notice here, they actually do make the distinction, as I described earlier, that was so important to make. There's two different categories for chloride versus chlorine. So chlorine is the neutral form, just Cl. Chloride is Cl minus. These have very different reactivity. So when there are important distinctions to make as to what type of element is being detected here, it will be noted in some way of how it's listed and categorized, okay? And if this is very overwhelming to you, we're not going to be looking at data like this in every lecture. The purpose of this is I just want you to have an idea of what is produced from a wildfire, what is liberated into the air as plant matter burns, as fire burns, etc. Okay, so let's keep going through this data set here. So like I said, what we have here is the PM 2.5 species that they're detecting, the relative concentration during a smoke wave that exists. So don't worry about the units on these numbers, just know bigger number is more particulate matter, okay? And then in this third column here, I have the percent change on a smoky versus a normal day. So meaning when a wildfire burns, what is the percent change in particulate matter compared to an average day, okay? So as you can see, some of these increase quite drastically, and some of these make a lot of sense that they would increase drastically. So here we have EC. So remember, this is elemental carbon. So I guess I didn't give you the acronym here, but EC is elemental carbon. That's just like soot particles. So that's carbon that doesn't quite burn completely. And this increased by 176% because of a wildfire, which makes sense because plants are largely composed of carbon and glucose. So it makes sense there's going to be a lot more elemental carbon particulate matter in the atmosphere as a result. We'll talk about this, why this is significant, what does it do, when we get to our third lecture, which will be on the troposphere and chemical processes that occur there. But let's just for now tuck this in our back pocket. We got elemental carbon as a big one that is produced from wildfires. We have chlorine. Neutral chlorine goes up by 300%. That's pretty massive. There's a significantly larger amount of chlorine in the air. We'll touch on this one in our second lecture when we talk about stratospheric chemical processes related to wildfires. Organic carbon, or OC, I don't know if I made that distinction on the previous slide. Hopefully I did. Let's see here. I did not, but organic carbon is often abbreviated as OC. So notice how elemental carbon and organic carbon get two different categories, and that's because the reactivity, the properties of organic carbon particulate matter are vastly different than elemental carbon, which we'll talk about in our third lecture. Hopefully I'm not annoying you too much by previewing the future, but really what I'm trying to do here is set the stage for what are we going to talk about, what is relevant here, and what are some things that are interesting, but we don't have time to talk about. Okay. So another one that will be important is here. So total nitrate. So remember, this is things like NOx, NOx. This goes up by 82%. So a lot of this, the reason why there's a lot of nitrates in smoke is because the air that we breathe has a lot of nitrogen and it has a lot of oxygen in it. If you mix these two together, which is inherent, because that's what air is composed of, there's a lot of N2 and a lot of O2. If we heat this up with, let's say, a wildfire, these can combine to form 2NO, which is one category, one type of NOx. So that's where nitrates typically originate with wildfire smoke, is just a lot of heat plus the N2 and O2 already in the air creates some NOx, and it can do some really devastating chemistry, but interesting chemistry nonetheless, that we'll talk about with our tropospheric lecture. And that just about covers everything we're going to touch on in the future. So like I said, there's some interesting things here. So 108% increase in potassium. That is certainly really interesting, but I don't think something that is really of concern by atmospheric chemists who are interested in the atmospheric processes that occur because of a wildfire. But anyway, just to reiterate what we're going to be touching on in future lectures, wildfire smoke contains a lot of chlorine, a lot of elemental carbon, organic carbon, which again, elemental carbon is just what we call the reduced form of carbon, or just carbon. And when we say organic carbon, we're talking about hydrocarbons specifically. So this is something that, like polycyclic aromatic hydrocarbons, will fall under this category. And then nitrates, which I already have here. NOx is also going to be another big one, okay? And this is just in the atmosphere from smoke. You might be wondering, well, what about all the ash that is left behind? What is that made of? So I have another data set for us to look at to set the stage for our discussions on water and soil chemistry, which is largely going to be impacted by what is left behind on the ground rather than what goes in the atmosphere. So for ash specifically, what we have here is another admittedly overwhelming data set. There's a lot of data here, a lot of information. But what these researchers did in this paper is they looked at the ash, or they analyzed the chemical composition of different ash from Australia, America, or the United States, Canada. This is Spain. I don't remember what this abbreviation was, but it's in Spain. This is also Spain and the United Kingdom. And just for your own interest, because I thought it was interesting, so I figured you all might find it interesting as well. This is the type of vegetation that was burned. So this is going to preview our fourth lecture on how does the type of vegetation impact the chemical composition and aftermath of a wildfire. So this is a eucalypt forest in Australia, a chaparral in USA, so think like inland San Diego County, perfect example of a chaparral, spruce forest in Canada, a heathland and a pine forest in Spain, and a grassland in the United Kingdom. And then one caveat I should mention about this data is that this chemical composition that is being reported in milligrams per kilogram or micrograms per kilogram, these would be trace elements, as we call them. These are specifically things that are water extractable or water soluble, meaning that what these researchers did is they took this ash, exposed it to water, and then measured the content of the water after the fact. So this is the stuff that will leach into water, into watersheds and natural waterways from ash, okay? So this is particularly the stuff that will be relevant to how does a wildfire contaminate groundwater, or, what compounds will be present in water after a wildfire. So we have a lot of similar categories. We have elemental carbon is across the board quite high. Something like DOC, so this is dissolved organic carbon. So this naturally will also be very high across the board. And notice here, there's actually quite a bit of disparity here. So if we look at a spruce forest in Canada, we have, orders of magnitude less in a pine forest in Spain. So why might that be? That's a really interesting idea and question we can tuck into our back pocket here. There's lots of sulfates, nitrates, very important things to consider with drinking water and groundwater. And then also for trace elements, well, there's a lot of iron, which is also quite variable. There's a lot of disparity here in terms of the amount of iron that is present in water. We're not going to touch on nickel at all, or at least I don't think we are, even though I don't know what's going on in Spain here, but there's a lot of nickel in that one area in Spain. And then if we have time, we'll touch on a little bit of lead as well, okay? So I understand this is a very overwhelming slide. This is a lot of information. What are we going to do with this? I guess all I'm trying to say is that there's a very vast and large and rich space in terms of wildfire chemistry. So my goal is to hopefully give you an idea as to what do all of these things do in various capacities and various locations, and give you an idea, give you more knowledge as to the atmospheric processes that occur post-wildfire, the soil chemistry, the water chemistry, the chemistry inside of us as we're exposed to these things, just more information about all of that. Okay, so hopefully I didn't scare you away with this information. I'm not going to ask you to regurgitate these numbers. I'm not going to ask you to know, what is a lethal dose in milligrams per kilogram of elemental carbon or sulfates or nitrates. Rather, like I said, just trying to spark your interest for the discussions that are to follow in subsequent lectures, okay? So if you have any questions on any of this information, you want to know more about the methods that these researchers used in this ash study or in the particulate matter study, I'm happy to provide you with the sources I used, and we can talk about, the validity of these results if you wish. But for now, I think I've droned on enough about particulate matter and chemistry of wildfire smoke and ash, so I will see you in our next lecture, which will hopefully be posted soon, okay?